Friends, today we are going to discuss a very important equipment used in India, more or less every industry, that is called cooling tower. Because in every fertilizer plant, your power plant, refrigerator, your refineries, chemical, petrochemicals, uh, and steel plants, so many plants, they are we are heat is generated during the chemical process, during the heat exchange. Heat will be generated, and if we have to release that heat, and for that the cooling tower is required. Otherwise, if you don't release this heat, you cannot produce product. So for that, cooling tower is required. This is the required. This is the only cheapest way where with this help of this equipment, cooling tower, you can release the heat generated in the plant and keep the production going on. So this is the schematic diagram. This is the heat exchanger of the plants. It is heat exchanger of the plant where heat is generated. We need to be cooled. The product need to be cooled. So what we are doing, that we are passing through the cooling water, inlet temperature will be less, and when it is cool this material, cool this fluid, it will temperature will hot, will increase. So this is cooling water in, this is cooling water out, and the plant your product temperature will come down. When this hot water of the hot cooling water will come to the cooling tower, it will cool through this air will pass through it will be sprayed from a series of nozzles are there at the top, and there is a fan. It will suck the air from the lowers, and when the the water droplet come in contact with the air, temperature will come down, and the temperature will come down, and then this temperature, low temperature cooling water through the pump, again we are sending back to the plant. But during this process, the some cooling water will evaporate from drip losses will be there. For that we need to make up. That's why from the make up water sources we have to make a make up water source through the pump. We are discharging the water to the cooling tower sump, so that water quantity will remain same. Now we'll show. I will give you some simple formula how to calculate the cooling tower load. Suppose we are running a power plant where from the boiler steam is coming at 101 degree centigrade and 505 degree 101 kg per centimeter 101 kg per centimeter pressure and 505 degree centigrade, and it exhausts the direct condensing type turbine, and the steam coming out from the turbine is 0.15 atta and 55 degree centigrade. So due to the heat expansion of the steam, some mechanical power will generate, and that will convert it into electrical power in the generator, and we are generating 125 megawatt power. Therefore the huge amount of the exhaust steam need to be cooled down and make steam to condensate. For that we have take out the latent heat of the steam, and that the cooling water is required. That is the cooling water in through condenser, and the cooling water out. The temperature will increase, but the steam will condense, and we are taking the condensate out into the further use of the plant. This is the schematic diagram of power plant where we are using steam to generate power and condenser to cool the steam, exhaust steam. Now, how to calculate the cooling tower load? Now, enthalpy of 101 kg per centimeter square 500 degree centigrade steam is 809. Enthalpy of exhaust steam, that is 0.15 kg per centimeter square, and dry-saturated steam is 609. It generates 125 megawatt hour power. So, if suppose M is the ton of steam required to generate 125 megawatt hour power, per hour, per hour 125 megawatt. So M into 809 minus 609, that is the steam expanding the turbine, and this is the heat per kg. So you have to convert it into kilogram, ton to kilo, 1000. That is multiplied by 1000. That is equal to 125 megawatt. That is equal to multiplied by 1000. That is kilowatt, and 1 kilowatt hour is equal to 860 kilocalorie. So multiply this. So this is the total heat. So you have to find. We have now, if we equal both and find out the value of M, the M will be around your 5 537 ton per hour. This much ton of steam is required at 101 kg per centimeter square and 505 degrees centigrade, and exhaust is 1.15 degrees centigrade, and 5 steam that is required to generate 125 megawatt power. 125 megawatt power, that is 4.3 megawatt metric ton per megawatt power generation. Per megawatt power generation. So now this was huge amount of steam, that is, you see the 537 metric ton per hour that need to be cooled, condensated cooled. For that huge amount of we have to cool that the latent heat had to be taken out, so that the steam become condensate. So what is the latent heat of steam at 115 ATA, 155 degrees centigrade, that is 571. 571 is your kilocalorie per kg of steam if you want to at 15 ATA, if you want to condensate it. So this much heat is latent heat. So how much, suppose here we consider M is the cooling water requirement. M is the cooling water requirement. So cooling water requirement. So and cooling water temperature will increase from inlet temperature is 35 degree, so the temperature will increase when you go, going out of the condenser, that will be 55 degrees centigrade. So M into 1 minute specific heat into 55 minus 35 into M is ton, so multiply by 100, because the latent heat is kilo per kg, so multiply by 1000, that is equal to latent heat into the quantity of steam. If we ignore the some sensible heat will be there, but we ignoring that. So this is the latent heat, and this is the cooling water requirement, which temperature will increase from 35 to 55 degree centigrade. So what is the M? Now M is equal to 537 into 571, that is 30662 meter cube per hour. So this is the cooling water requirement to condensate 537 ton per hour steam at 0.15 kg per centimeter square, 55 degrees centigrade. So if you convert it into mass, that is a gallon per minute, then 1 meter cube per hour is equal to a gallon per minute at a meter cube per hour is equal to 4.403 gallon per minute. So this much meter cube per hour will be how much? Now 1350078.68 gallon per minute. So this much cooling water is required. This much cooling water is required, and that much cooling water need to be cooled from 35 to from 55 to 35 degree centigrade in cooling tower. So then cooling tower, normally we refer the cooling tower unit, that is per metric ton, and that is calculated. So multiply the formula is 500 times water flow times of temperature difference divided by 15000, or 500 into Q, we have to gallon per minute, then delta T temperature range of the difference in Fahrenheit divided by 15000. Here the temperature difference will be this is the quantity of gallon per minute I have calculated earlier, and this is your temperature difference. So you have to use this formula to find out the ton of cooling tower. Cooling tower is specified by unit specified by ton. So 500 into this much, your this much will be your heat. This was your will be gallon per minute of your cooling water. Then this is your BTU, degree Fahrenheit. This is the degree Fahrenheit per hour. Degree Fahrenheit per BTU per hour. So the ton of CT will be 500 into 3600. This is the value of this is the total value. This is the this value. So into 45 degree Fahrenheit divided 150. That is the cooling tower ton will be how much? Now 202369 ton of cooling tower is required to generate 125 megawatt power. That is theoretical. Apart from that, it will be further more, but this is the cooling tower capacity. This is the cooling tower capacity. We are define the cooling tower how size by this metric ton. So how this figure has come, 500 figure has come, that will discuss now. This formula 500, because we have to know that heat is taking out taking out by mCp into delta T. M is the Q is the heat, that Q M is the your quantity of cooling water required. Cp is the specific heat. There is the temperature difference. Inlet minus outlet. So you have to here you see the 500 into how this figure 500 has come, that will first discuss the 500 how the figure has come. Now this is density of water is equal to, now this is approximately 8.33 pound per 33 per US gallon, US gallon, and US gallon. So density. So and time conversion is equal to, 1 hour is equal to 60 minutes. So specific heat is equal to 1 BTU per pound per degree Fahrenheit. So multiply this, if we multiply this is 8.33 into 60 is a minute, 1 hour is equal to a minute, 1 BTU per 1 BTU, then the value will be around, if you multiply 8.33 into 60, it will be 499.8. That's why the 500 figure has come. This 500 figure has come like this. And then 1500, how this figure has come? Now, because we know in the refrigeration, we know refrigeration load we defined as the 12 in ton, that is one refrigeration ton, 1 ton means 12000 BTU per hour, which means the heat is required to melt 1 ton of ice 24 hours. This is the heat we require per hour to convert 1 ton steam in 20 to 1 to heat required to melt to 1 ton of ice in 24 hours. This much heat is required. This much heat is required. But in cooling tower, it is slightly more, because the cooling tower itself, due to its manufacture, it will take some heat. That's why 0.25% more heat you have to add. That is 1200 into 1.25, that is 1500 BTU per hour. That's why the 1500 figure has come and 500 figure has come due to this factor 8.33, that is your gallon per minute density, water density, and 60 is your here you see the gallon per minute, convert it gallon per minute, and 60 is your per hour, means 60 minutes. That's why this 500 figure has come. So I think figure has come. So I think I have discussed in detail how to calculate the cooling tower load, because you have to find out how much heat is required first, how much steam is required to be condensate, how much steam, how much cooling water is required to convert the steam into condensate, how much heat is required for heat exchanger, other chemical heat exchangers to lowering a temperature. That calculation, once you get this value of the cooling water requirement, then you can calculate the size of your cooling tower, that is defined by metric ton, that is 500. We have shown you the formula, that if you put this formula value of Q delta T divided by 1500, 15,000, 500, numerator is 500. That also how the factor has come, that also I have discussed. So you can find out the cooling tower capacity or cooling tower metric ton, how much cooling tower is, how much size of the cooling tower. So I think if you go through the slides and understand the description, the way we have explained, I think your concept will be totally clear. And if you are satisfied with this discussion, I think you will like this channel by make a like mark, my TK like comments, and subscribe it, so that the future also we are going to, for few days we are going to discuss about the type of cooling tower, different type of pin. There's so many so many um, uh, post will come in the cooling tower. Your concept on cooling tower will be clear. Uh, so if you are satisfied, you also requested to share this channel to your friends who are studying in final year mechanical engineering, or if you are servicing in a plant or industry. There also you will your, or you are going to face some interview board, then it will help you to understand. uh, and not only this is we have discussed here how to calculate practical aspects, experience also you will get in this channel. So we request you to subscribe and expose it to more into your friends. If you have any doubt, you can contact me, or you can convince your management so that a lecture can be arranged online by mutual discussion. Thank you very much.